students. Welcome to the EN 401 lecture on soil stresses and capacity. Here's the roadmap for our lecture. We're going to talk about soil bearing stress and capacity. We'll talk about soil strength, soil stresses, and then the relationship between soil stresses and soil strength. So what is bearing capacity? So bearing capacity and bearing stress is how much normal stress can a typical soil hold before it yields. Bearing stress and capacity deals with superficial loads, so loads very near to the surface and soil failure very near to the surface. So the types of structures or analysis we'd see would be, bearing capacity for roadways, bearing capacity of subgrade for concrete pads, bearing capacity of soils where we're going to put some containers, and maybe bearing capacity for some area where we're going to put vehicles. Bearing capacity and bearing stress, it's not really a suitable method to determine how strong a soil is for the design of buildings or bridges or other large pieces of civil works. We'll look at the type of soil stress and strength that is used to do the analysis for those buildings later in this lecture. So for a good example of where bearing capacity is useful, go ahead and watch this video here, driving on sand. You'll see that the bearing capacity of the sand is a big factor in how easily you can drive on sand. So how do we calculate bearing capacity and bearing stress? Well, as the previous slide said, bearing stress is a normal stress. So our normal stress equation is what we'll use to calculate bearing stress. So sigma is equal to force divided by area. So sigma is our bearing stress. The two types of bearing stress we can talk about is the ultimate bearing stress, so the maximum amount of stress that we can place on the soil without the soil failing. But that's probably not the best measure to use, just because we don't want to push things totally to the limit. We want to leave ourselves some margin of error. So whenever we calculate bearing stresses and capacities, we always use the allowable bearing stress of the soil. That way we give ourselves a margin of error, factor of safety. So this table here shows the general relationship between soil type, so USCS soil type, which we completed in the last lecture, so you should be able to analyze and classify soil, and its allowable bearing capacity, right? So that's one of the important pieces of classifying your soil, is it'll tell you essentially what the bearing capacity of that soil is. And we see that at the top of bearing capacities for soils, we see that we have gravels up here. So our coarse grained soils are our strongest soils. And going all the way to the bottom are fine grain or cohesive soils, right out here at the bottom as our weakest soils. So with the soil classification, you can find the allowable bearing capacity using this chart here, and you can figure out if your soil is going to work for the situation that's been given to you. Soils develop their long-term strength via two methods. In cohesionless soils, purely cohesionless soils, they develop their strength via friction between the particles. So only friction between the particles. And our cohesive soils develop their strength purely through cohesion. All right, so the total strength of a soil is going to be the sum of those two. So if you have a mixed soil with cohesive and non-cohesive materials, you'll have some combination of friction between the particles and cohesion that gives that soil its total strength. So we defined the friction between particles with this angle of internal friction, phi. All right. So small values of phi mean that the soil is not very strong, has low friction between the particles, and high angles of phi mean lots of friction between particles and the soil is stronger. So practically speaking, if we were to look at this pile of sand over here, this angle here, phi, which would be the internal friction angle or the angle of repose, that changes with the strength of the soil. So, really strong soils will have a great angle. So this is a pretty strong soil because this is a pretty large angle. And low friction soils would have smaller angles. So that means if you have a low friction soil, your pile of sand to make it taller would have to be much, much wider. Whereas high friction soils, you could get a taller pile of sand without such a wide base. So typical values for phi are between 15 and 45 degrees. So 45 degrees would be a very high friction cohesionless soil. Now our cohesive soils, if we had a purely cohesive soil, they would have no internal angle of friction and they would only gain strength through cohesion. So pictured here, we have some blocks of clay, and those clays, we can see they actually, if almost defy gravity here, right? They can go straight up, perpendicular to the level ground here, and that's because they have cohesive strength, but they do not have, they don't really rely on friction between the particles to develop strength. So how we measure the coefficient of cohesion for a clay is with this symbol C. We just call it C. And for non-cohesive soils, so for coarse-grained soils, they don't have any ability to adhere to each other, so no cohesion in coarse-grained soils. So sort of a mental thought on that is just imagine you're holding two pieces of gravel in your hands and you put those two pieces of gravel together. They don't stick, right? They just act independently of each other. Whereas in clay, right, this clay here is made up of billions and billions of tiny little particles, and they're all stuck together, which allows that clay to be stacked up vertically like it is in the picture. So we know that soils gain their long-term strength via cohesion and friction between particles. So the way we determine how strong a soil is we conduct a Mohr-Coulomb analysis. And the end product of a Mohr-Coulomb analysis yields these semicircles here. So these are called Mohr's circles. So we're not going to get into how those are developed. But the Mohr-Coulomb analysis gives us those Mohr circles. And then if we connect the tangents of those circles, which I'm highlighting red here, but it was that black line, right? That gives us our strength envelope. So we can see with this Mohr-Coulomb analysis here that as effective stress increases, our shear stress also increases. So as long as our stresses are below this envelope here, what we call the rock strength envelope or soil strength envelope, this test is also used for rocks. So as long as we have stresses that lie in a region below that envelope, our soil or rock will not fail. We can see as effective stress is going up, the available shear stress is also increasing, right? So if we have an effective stress of 8,000 or so psi, our available shear strength ends up being about 6,000 psi. Whereas if we go down to, let's say, no effective stress, right, we end up with just our C value, our y-intercept, so we're down to 770 psi of strength with no effective stress. So more effective stress essentially means more strength, A good mental exercise for this is, take your hand and place it gently on your desk, and then move it left and right, and it moves fairly easily if you don't push down very hard. If you do that test again, but then push down as hard as you possibly can and try to move your hand left or right, it doesn't slide very easily. So that same phenomenon happens in soils. So the more stress that's being applied to the particles, the more friction between the particles, so the stronger essentially the soil becomes. So big note here too is that water has zero shear strength. So by adding water to a soil, you can't really make it any stronger, because water only it doesn't have any ability to add shear strength, because it itself doesn't have any shear strength. Imagine trying to make a pile of water like we had a pile of sand on that last slide. It would just make a big puddle. So water does not help with the strength of a soil. All right, so we need to figure out how to calculate effective stress so we can kind of sort of determine, how strong our soil is going to be for our application. So to calculate effective stress, we have to kind of go through a process. So the first part of the process is to calculate the total stress. So the total stress is equal to all of the weight on top of a particular soil particle. All right. The second piece is, all soils pretty much have water in them, and that water creates a buoyant force on soil particles. And we call that buoyant force on soil particles the pore water pressure, right? So if total stress is the amount of weight on top of a soil particle, and pore water pressure is the buoyant force, right, then the effective stress is the relationship between total stress and pore water pressure, right? So total stress is helping effective stress, and pore water pressure is hurting effective stress. All right, so now we're going to figure out how to calculate total stress, pore water pressure, and effective stress. So we'll start with the easy one. We'll start with pore water pressure because we've already seen this before. So pore water pressure is the same calculation as hydrostatic pressure, which we covered in the Archimedes lecture. So we know that hydrostatic pressure is equal to the depth below the top of the water times unit weight of the water, right? So we use this symbol here, mu, for pore water pressure. That's equal to the gamma of the water, and we typically use gamma of fresh water times the depth of water. All right, so we'll use this picture here on the right to kind of look at this. So if we're analyzing the pore water pressure at this point x, right, we know what gamma fresh water is. That's 62.4 pounds per cubic foot, right? And if we know what this depth is here, we call this depth z water, then we can calculate the pore water pressure. So then we'll cover how to calculate total stress. So total stress is equal, so we use sigma for total stress. It's equal to the sum of however many layers of soil you have above your reference point. So we'll stick with the same reference point here, of the gamma soil, or the unit weight of the soil, times the depth of that soil layer. All right. So in our soil profile here on the right, we have two soils. So soil 1, this will have a gamma, we'll just call it gamma 1, and then we have soil 2 here. This would be gamma 2. Now remember, these gammas include water. So the unit weight of soil, remember, includes water. So it's not asking for gamma dry, it's asking for gamma soil, which includes the water already. So you don't have to add gamma fresh water to this gamma to get gamma soil. The gamma soil will already be given. So in this particular example, if we wanted the total stress of the soil, it would be equal to gamma 1 times Z1 plus gamma 2 times Z2. That's times there, right? And we already did our calculation here for pore water pressure, which is mu is equal to gamma fresh water, and we see that our Z water and our Z2 are the same thing, so we'll just make that the same value in our equation. So times Z2. All right, and we remembered that total stress is equal to the amount of weight on top of our reference point, so that one's going down, and pore water pressure is a buoyant force, so that one's going up. So that means effective stress, so we use this sigma prime here as effective stress is just equal to the total stress minus the pore water pressure. So it's equal to sigma minus mu, and I'm not going to write that equation out. I'm not going to combine these two equations for sake of brevity, but you could do that if you wanted to, and this will give you your effective stress, right? So we see that if pore water pressure is really high, we could actually turn our effective stress down to 0, right? If we have more pore water pressure than total stress, then our effective stress will go to 0, and that could be bad for the soil strength, right? All right, so now we know what effective stress is. Let's look at the relation between effective stress and strength and why it's important. Right, so we know that effective stress and strength are linked, right? So more effective stress equals more strength. And we know that pore water pressure has a negative effect on effective stress, right? So more pore water pressure is bad for soil strength. So if we have too much pore water pressure and we get effective stress to go down to 0, then we also end up with 0 soil strength. So what does that mean for anything that's placed on those soils that have no strength? Well, they're just gonna sink in. All right, so we call that phenomenon when our pore water pressure is really high and we lose strength. We call that liquefaction, or you've probably heard of it as quicksand. Right, so it's an issue where the pore water pressure gets increased above the total stress, and then effective stress becomes 0, and essentially your soil turns into water, and whatever's on it sinks in. So go ahead and watch those 2 videos. And this paragraph here sort of describes why it happens in sands. So the reason it happens in sands is one, sands don't have cohesion, right? So relies totally on effective stress to provide strength, and if the sand is fine enough, it has a low permeability. So what happens is when a load is applied to it, the water can't escape fast enough, so the water takes all the load, sort of like when you squeeze a sponge, right? If the water couldn't escape, you'd just be sort of squeezing the water, but when you squeeze the sponge, you put pressure on the water and the water squeezes it out of the sponge. But in the soil, the water, it just can't escape fast enough, so it ends up carrying the load. So what happens when it carries the load is the pore water pressure goes up, and the pore water pressure will end up going above the total stress, making effective stress go down to 0, and then that soil becomes a liquid. All right, so here's example 1 on bearing capacity. So go ahead and watch the example video on this one. So we're just looking at bearing capacity on this one. In example 2, this is a soil stress problem. So you need to calculate effective stress, right? So before you watch the video, go ahead. You can see that we have 3 layers, right? So you'll have to use do a summation of the total stress for all three of those layers. And remember that seawater is the depth of water to above our point. All right, and here's a review. Thanks for watching.